I'm going to talk a little bit about practical applications of turn lanes in urban and suburban corridors. I'll talk a little bit about some of the same things probably Marcus had touched on, so I'll probably rush through some of these and probably save some of the good stuff for the end, or what I think is the good stuff. All right, so when do we need right turn lanes, or left turn lanes for that matter? Well, we need right turn lanes. We've got guidance in the Access Management Manual. You're probably all very familiar with that. Speeds of 45 miles an hour. If you got more than 50 vehicles turning right, we expect the developer or the private developer to install a turn lane. And it also provides guidance as far as where we need to spend money to install particular turn lanes. Speeds less than 45, you can get down to 60 vehicles per hour. There's actually other factors listed. Of course, crash experience, limited sight distance, heavy through volumes, because anybody turning right from a roadway is going to be impeding the traffic behind them, and heavy truck volumes. If you've got any of those items, you could go the extra mile and install a turn lane just to solve a potential operational problem. For left turn lanes, the Access Management Manual says basically all conditions. And that makes a lot of sense. A left turning car that has to filter through gaps in the opposing flow is going to have a much bigger impact on traffic behind it. So the basic components, we've kind of already talked about those. Queue length or storage length, how do we normally derive those as engineers? I would recommend using an analysis software, either highway capacity software, Synchro, VSIM, whatever you're capable of using as a traffic modeling. Basically, just be sure that you're using the appropriate traffic projections. That's if we're designing for a 20-year horizon, then we're going to have a traffic projection out there that's a daily traffic volume. Then we're going to convert that with a K factor. So we're going to get down to some kind of number at the end by the time we apply some turn percentages, and it's probably going to be 143 or 142. Don't worry about the one digits on those types of numbers. Just round it up and use that number, because I wish somebody would do a research project on the significant digits of traffic volumes, but that's something that we don't really mess with a lot of. Minimum storage length on a right turn, of course, is 30 feet. That's basically enough to store one vehicle. We assume a car is 25 feet, so that's 25 feet plus another 5 feet. So if we're using trucks, let's say you're designing a turn lane to feed into a major distribution center that basically receives only trucks, you'd want to consider a more appropriate design vehicle when you're looking at that storage length. There is a formula in the Roadway Design Manual you can use to estimate your length of storage needs. It'll work for either left turns or right turns. The L equals your volume, vehicles per hour, over N. And in this case, if it's unsignalized, you use 30 for N, which basically represents the traffic arriving in a 2-minute time frame. They use a factor of 2 to account for storing more vehicles than are possibly going to arrive, or to make sure we're not going to overfill the storage space. And S is what they're using for the vehicle length. And of course, S can be adjusted over here in this table by taking the percent trucks into account. And obviously you can see the impact's pretty great. If you got less than 5% trucks, you use a 25-foot vehicle. If you're getting up closer to 20%, you're up to a 40-foot length vehicle. Now, taper length's that other component. I would say you can always shorten your taper length, but you probably don't want to lengthen it too much. I forget where I was driving the other day, but I was in a location where there was just a massive expanse of asphalt because there was a super long taper. You get out there in that situation, drivers don't seem to know whose lane they're in. So it's better to keep that a little shorter, from my opinion. Of course, use a straight line taper on most of your roadways. If you're using a curb roadway, then you might want to consider a set of reverse curves that wind up with taper lengths similar to these that are presented. And those are all straight out of the RDM, or Roadway Design Manual. Deceleration lengths. We've got new research here, so this is just totally worthless now. But it's what we're going to use now, and it'll take a while for the Green Book to be updated, and then the Roadway Design Manual will be a few years behind that. So these will probably work for quite a while. As Marcus mentioned, the ideal speed differential is 10 miles per hour. And the speed differential, we're talking about the difference in speeds primarily in that lane that's either the right-hand lane for a right turn lane or the left-hand lane for a left turn lane. Whenever that speed differential gets too excessive, it can become a problem, but ranges of 15 and 20 miles per hour are acceptable. I will say that I have been able to calculate the 10 mile per hour speed differentials, but if you look at the table for 15 and 20, someone kind of just shifted the values up a little bit. I haven't quite come up with the same calculations as the roadway design manual, but I'm presenting that information today. Crash potential, it increases basically exponentially as the speed differential increases. That's why turn lanes are really so important for crash rates. IT's Traffic Engineering Handbook, 6th edition in 2009. If the speed differential is 30 miles an hour, you're about 23 times as likely to, or more likely to get in a crash than if the speed differential is 10 miles per hour. When that goes up to 35 miles per hour as the speed differential, you're up to 90 times more likely to have a crash than at 10 miles per hour. So it really is it keeps getting worse and worse the bigger that speed differential becomes. As Marcus mentioned, these are the values in the green book. When you're in the left turn lane, you're decelerating about 6.5 feet per second squared. Well, to me, I don't know what 6.5 foot per second squared looks like or feels like, but I do know what emergency braking kind of feels like. So if we're about 15 feet per second for emergency braking, normal deceleration would be about half of that. So I can kind of feel that and understand what that means to a driver. Another interesting bit of information is similar to some of the information that Marcus had. The 85th percentile deceleration rate that was presented by ITE and Dr. Stover's Transportation Land Development book was 6.7 feet per second squared. The 50th percentile was up to 9.2. So, half the drivers are willing to accept a 9 foot per second squared deceleration rate. So they're getting pretty close to more or less emergency braking. Now, I saw Marcus had some numbers of 24, so that must be serious emergency braking with some nice ABS systems working as well. So those are all good things when it comes to trying to provide adequate deceleration. That means deceleration rate could actually be, or the deceleration lengths could be a little bit shorter. Now, a lot of times in our urban areas, that deceleration length gets used up, maybe in the peak hour or the peak periods when we actually don't have enough queue storage to handle all the traffic. The queue will basically start filling up into that deceleration length as well. And in an urban area that's heavily congested, that might be okay because traffic speeds are definitely probably not near the design speed. But of course, we're always trying to design out there and get us up closer to the ideal conditions. One thing that wasn't mentioned earlier, of course, is the width of the lanes. These are values straight out of the RDM as far as, I just have kind of summarized it. Less than 30, 10 miles an hour, 35 to 40, 11 foot of width, 10 foot of width on less than 30. And then when speeds are more than 45 miles an hour, I say 12 foot is a minimum lane width. It is interesting, there are some values that are allowed for less than, urban streets with a low speed of 30 miles an hour, a 9 foot turn lane. That's probably okay. This one's kind of interesting. If you have a 60 mile per hour local street, the RDM would allow you to go down to a 10 foot width of turn lane. I'm kind of opposed to that, having experienced kind of a 9 or 10 foot turn lane next to 60 mile per hour traffic before. And when a geo can come by and your vehicle rocks because of the force of the wind of the vehicle passing, that makes me uncomfortable as a driver. So I would try to stick with more or less a 12 foot width. It's very similar for left turn traffic. The only real difference is in the storage length. The minimum storage length presented in the RDM is 100 foot of storage. But of course, I'd recommend you go ahead and calculate it using one of your traffic analysis softwares. There's also some good values in the TxDOT's Urban Design Guide, which Kay had a hand in authoring. There's some values in there of, you've got opposing through traffic versus left turning traffic, and so that helps you get a value out of a table for what your left turn lane length should be or your storage length. And of course, it can be estimated with that formula. What's going to obstruct you from getting to your desired left turn lane length? Once you figure out what that is, well, we see a lot of things in the field. Drainage features, a large culvert with head walls pretty close to the roadway can be a cost obstruction. we either have to lengthen the culvert or do something like that in order to put the turn lane on top of it, or we have to shorten the turn lane. Bridges, that's a little harder to deal with when it's in place. You've got a bridge rail there. You're not likely to widen the bridge to squeeze in a few more feet on a turn lane. Trees, heritage trees, as we call them in my neck of the woods, that could be a problem. Restricted right-of-way can prevent you from being able to widen the roadway enough. Of course, adjacent property lines, that can be where the right-of-way comes into play. Transmission towers for utilities, communications lines, a railroad crossing, and of course, one of the most prevalent is probably adjacent driveways or intersections. We see more conflicts with adjacent driveways when it comes to providing the desired turn lane length, more so than anything. So one of the things, of course, providing adequate turn lane length is very important for operations and safety. But, one of the things that I always say is that any length of turn lane is better than no turn lane. So if you're forced into a situation where you can only provide a certain amount, then provide that amount and move forward. Now, a few examples. I'm glad there was an example of the Churning Roadways there. This is a location, I'm going to say up front, it fits that non-pedestrian friendly type application. It's a nice big turning, sweeping roadway. So that means you don't have to have as much deceleration rate or deceleration in the through lane, because that turn is going to be made at 20 plus miles per hour. But then again, that's also not a very pedestrian friendly type of operation. In this particular location, given the freeway frontage road, the network, the types of businesses that are in here, there's really not as much pedestrian activity as there might be in other parts of the urban area. So in this case, this particular design does seem to fit the context of its present location. I'm not going to say that'll work out in the future, but it does today, so it's a suitable design. Here's a kind of a quandary I'd mentioned earlier about having multiple driveways and turn lanes that would extend across the driveways. I've seen this done multiple different ways. I've seen people use multiple short turn lanes to achieve this. In this case, some kind of deflector allowing people to turn right and turn out. I'm more inclined to say, in a situation like this, I would prefer to have more of an auxiliary lane, is what I would call it, all the way down across all the driveways. And this is actually another driveway. I guess it was in the process of being reconstructed. So that's a right turn lane that goes all the way up to this intersection, but that could be another driveway as well. And in that situation, since traffic in that right turn lane is expected to be slowing down somewhat, I would anticipate that the drivers on the driveway recognize that particular driver may not be turning into that particular driveway, and they may be turning into a downstream driveway, and make the appropriate decision not to pull out in front of them. If we don't have the adequate deceleration length, then of course we're going to introduce more conflicts in the through lane or in the adjacent through lane. I'd rather that conflict occur in that slower right turn deceleration lane. Now, of course, I have no research to back that up. I've seen no research to back that up. It's basically more a matter of personal opinion, and I'm sure in this room people would have debating opinions about that. And one other thing I wanted to mention involves left turn lanes and the use of offset lefts. It's an alignment issue. What's called a negative offset. If you have a typical raised median situation, the left turn driver, in this case, view of approaching traffic can be obstructed by a left turn driver sitting in the opposite left turn lane. Of course, when it's lined up more straight across, his view is a little bit better. But if you put in a positive offset, and of course you've got to have the median width in order to do this, you can actually open up his view angle to see approaching traffic much better, so he could actually make a safer turn through those gaps. This was an application where we actually applied an offset left to solve a visibility problem. This was a middle school. This is the middle school driveway. basically an arterial roadway, and I'll ask you to ignore the fact that this turn lane was obviously way too inadequate for any kind of school, almost way too inadequate for any kind of driveway application. There's a crest vertical curve right about this point. I'm gonna call this westbound, this is gonna be eastbound. And the westbound lanes are actually about 4 feet higher than the southbound, or the eastbound lanes in this case. You know, the solution was come in and basically do more of an offset left, even though there's no opposing traffic. In this case, the offset left overcomes the side obstruction created by the vertical curve by allowing us to bring the left turn traffic up to grade with the opposing traffic so that they can see the approaching traffic. And of course, when they leave, they're kind of going downhill through this little section and merging in with traffic with a yield control. So, in summary, you should provide auxiliary lanes wherever possible with storage and decel where you can. And it's okay to use the 20-mile-per-hour speed differential when you're doing that. I would recommend using taper lengths of the design values that are in the RDM. When you've got obstructions, just provide as much turn lane as practical if you can't remove the obstruction. And consider using offset lefts for safer left turns.